I'm using each side 2 times. So for instance, this one right here is being used as the right side of this trapezoid, but it's being used as the left side of this trapezoid. So except for the very first one and the very last one, I'm using each side twice. So when you see the formula, hopefully that'll make sense. And then we're going to do another one, Simpson's rule, where the tops are curved, which might make a little bit more sense because we're looking at the area under the curve. So let's make the tops not flat, not diagonal, not straight segments, but maybe curved segments, parabolas. And I will show you the formula for that. You don't have to know necessarily geometry for that. Okay, so that's where we're headed today. We want to get some examples in. But, so we've divided, so far we've divided the intervals into n number of sub-intervals of equal length. That's very helpful to do it of equal length. You're not always guaranteed that. Sometimes in tables it's not equal length. So you can't put the width out. You got to do width times height every time. So change in x, in order to figure out what that width is going to be the interval b minus a over n, how many shapes, rectangles up to this point. And then I'm going to add up from 1 to however many. That means add up the function value for each value of x, change of x. This is height, width. Add that up. Height at that value of x, width. The width is going to be the same every time. Height times width. Just add up each one. That means add up all of them. Okay? These are called Riemann sums. Then, if f happens to be positive, then the Riemann sum can be interpreted as the sum of the areas approximating, so that can be interpreted as the sum of the areas approximating rectangles and can be referred to as the area under the curve from A to B. If f takes on both positive and negative values, meaning it might go under the x-axis, then the Riemann sum is the sum of the areas of the rectangles that lie above the x-axis less the areas below. So it's giving you the net area when you do this. So any of the area that's below the x-axis gets taken away from the area above. And so when you're looking at the final answer, you're getting the net. So it's possible, if you have more area underneath the x-axis than above, you could get, hey, I got an area that's negative. This doesn't make sense. Area can't be negative. Yeah, it's telling you most of the area is underneath the x-axis. The problem is, if you want the total area, you got to take whatever's negative, absolute value, add it. So be careful. That's giving you the net area. Okay? We okay with that? You may not have seen this before, but it's in the notes. Okay. As the number of rectangles gets bigger and bigger and hopefully approaches infinity, then we're going to get closer and closer to the exact value of the area under the curve. And this is called the definite integral. So, if we add up all of my rectangles, height times width plus height times width plus height times width, hopefully that's the same, we can just pull that out. Height, 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 height. Add all those together, and then at the end, multiply by the width. And if you can imagine doing that an infinite number of times, you get this thing. The integral from A to B of your function, dx takes the place of change of x. Since this is the same every time, we're going to change it to dx. And when we have a definite integral, the dx is just going to mean, hey, that's the variable we're interested in, change of x. Okay? Some terminology here, okay? We might say integrable. That just means I'm able to take the integral. An integral of a limited sum of limited sums. F of x is called the integrand. big deal. It's probably the only time you see this word. And A and B are called the limits of integration. This is important. A is the lower limit, B is the upper limit. So that means I'm going from this to this. Okay, from left to right. So that's the limits of integration. That you'll see again, this, and we'll probably use that term. That means I'm able to take the integral. This thing right here, the integral from a to b of f of x, d of x, it is one value. Because this will give you one numerical answer, which is the area under the curve. Okay, it's one symbol, one numerical value. Just like the square root of something, you're gonna get one value for that. But it's got a bunch of things in it. Or sine 30 degrees, you know, it's got different parts to it, but it's gonna be one answer. This is gonna be one answer. Okay, and the dx instead of the change of x. The dx, because we got an infinite number of these things. So if we got an infinite number, if you're thinking infinite number, that's not very wide. So dx takes the place of the change of x. It just really tells me that's the variable I'm interested in. So if I have different variables, it's nice to know that, oh, this is the one I'm supposed to focus on, dx. And the process of calculating an integral is called integration. Anyway, a lot of integral type terms here. But, well, we'll go through that in more detail. This is just the first time you're seeing it. Okay. Let's see, anything else I want to, oh yeah. So we've done left endpoints, right endpoints, and we did the midpoint, right? Everybody has got practice with this, right? Left, right, and midpoint? Yeah. Okay. So here's an example, midpoint. And here's an example of what we're going to introduce now. What if I make the top diagonal? Still flat, but diagonal. So that it goes from the left side of each rectangle and the right side. See how this leaves like corners sticking out? This is using both sides. Well, it doesn't. It means it's not going to be horizontal anymore. I don't have a rectangle. I have a trapezoid. Here is the formula for adding up a certain number of trapezoids instead of rectangles. Let me pull this up. So the integral of f of x dx from a to b, I can approximate that, just like I did with rectangles, with trapezoids instead. And as how many trapezoids do you want? Probably more trapezoids, the better. We're going to tweak it because it's not rectangles anymore. This is just an approximation. Of course, the bigger the number n, the more trapezoids I got, the better the approximation. But we were used to having the change of x outside because that was the width every time. We're doing equal widths, we still are, times the height at different values of x. Well, we're still doing it, but remember, you gotta take the change of x here divided by 2. Change of x divided by 2. That's because we're using both sides. We're using both sides of the x's, or both sides. We're using this side and this side. This side and this side, this side and this side, and this side and this side. Before we just use either this, 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 and this, or this, 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 and this, or midpoint right in the middle. We only used it once. Okay? So remember, if you want to write this down, change of x over 2. It's still going to be the same. It's still going to be the same. Divided by 2 because we're using both sides. And then inside we've got this. What's the height of the first side? Okay, that makes sense. Plus, what's the height of the second side? But notice I got 2 times that. because that second side is the right side of the first trapezoid, it's the left side of the next one. And then I got 2 times this one, it's the right side of this trapezoid, it's the left side of this trapezoid. So I'm gonna use everything after that first one twice. So I got 2 times that outcome, 2 times that outcome, plus 2 times the next one, 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 until I get down to the final one. Then I'm gonna use 2 times this one for this for this trapezoid on the left, this trapezoid on the right, so this side gets used twice. The very last one gets used once. Whew. That's the formula. The changes. Change of x divided by 2, not just change of x. Change of x divided by 2 on the outside. You're still gonna plug in x's, different values of x's. But the first and the last one, you're only gonna do it once. Everything in between, you gotta multiply by 2. Or do it twice. It's easier to multiply by 2 than to do it. And we figure out change of x's anyway. Okay. Have I got this puppy down? Trapezoid way. Okay. Boy, you thought the rectangles were tedious. Let's see, trapezoids. Let's see, actually, we'll do 1 and 2 here in a minute. Between the trapezoid and the midpoint, actually the midpoint is a little closer, strangely enough, than the trapezoid would, but it doesn't matter. We'll look at Simpson here in a minute. Hold on a second. Yeah.
We never got it.
Oh, I never did. Okay. You didn't. I'll put these. I'll give them out. Good. That's good. Oh, but you want to take notes, right? For examples. Take one down, pass it. 99 bottles of beer. Okay. Not a lot of examples on here because they are tedious. Tedious meaning time consuming. Not hard, just like it takes. So, we don't have all that many examples, but let's use the trapezoid rule and the midpoint rule with n being 5 to approximate this integral. Okay? So, if I'm going to use, the first one is the trapezoid. So the integral from 1 to 2 of 1 over x dx is going to approximate, we're using trapezoids in 5 of them. It'll look like that. Well, I gotta figure out what the width of each one is going to be. Yeah, the change of x is going to be, let's see, I'm going from 2 to 1, 2 minus 1 over 5, so that's going to be 1/5. If you like decimals better, that's 0.2.
Hey, Mr. What's dx stand for again?
Dx, when it's written in this one, takes the place. The integral will have dx. That takes the place of adding change of x. So if we're adding them all up, we want the change of x, which is going to be 0.2. And dx, we'll get to that later, but we're approximating right now, so we have to use this change of x over there. which is 1/5 or 0.2. And if I'm gonna do the trapezoid rule, remember that formula. The trapezoid rule is the change of x, 0.2. But remember, I have to use both sides of the trapezoid, or most of them, divided by 2. I can't just pull out 0.2. Okay. Then I have to do whatever f of 1 is, because that's going to be my first one, right? If I want to draw a little picture, I'm going from 1 to 2. What is that? 1.2, 1.4, 1.6, 1.8. Right. There's my 5 pieces. And so that's going to be 1.2, 1.4, 1.6, 1.8, 2. There's my 5 pieces. So the first one I got to plug in is that one right there. Then I'm going to plug in this one. So I want to add, plugging in the next x is going to be 1.2. But I got to do that twice because it's going to be this side of the trapezoid and this side of the trapezoid. So I'm using that piece twice. So I'm going to multiply by 2. And then I'm going to do 2 times the next one, which will be 1.4. 1.2, 1.4, next one's going to be 1.6. I'm going to plug in. What's the height when x is 1.6? What's the height when f is 1.8? And of course that's going to be that one, so I've got the side going to this one, and I got the side going to that one. The last one is 2. I'm only using that side once. And since they're the same width, width times height, width times height, width times height, I'll pull the width down, adjust it by dividing by 2. Okay. So if I'm doing this in pieces, of course you can put all of this in your calculator. But just to show you, that's going to give me 0.1 outside. And then I'm going to have to put, what was my function, 1 over x? So 1 over 1 plus 2 over, because it's going to be 2 times 1 every time. 2 times 1 over 1.2 plus 2 times 1 over 1.4. So 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 1 over 2. Right? Because I've got 2 times this every time. 2 times 1 over whatever that is. Just using the function. Thank God we got our calculators, right? You just pop all that in your calculator, kind of tell you what you're gonna get. I just skip to the chase. Use my calculator, pop it in there. I got 0.6956. College Board likes minimum 3 decimal places. Sometimes I give it, yeah, sometimes they can truncate it. So if you said 0.695, that's fine. If you said 0.696, that's fine. So I'll just keep it 6.9. What was it, 5.6? I don't like the truncating, but they'll take it. They figure by the 3rd decimal place. And that's square units. They give you centimeters or meters or something. Okay, so that's the trapezoid. Now, B says let's use the midpoint rule. So, I'm going to estimate from 1 to 2. I'm going to estimate integral, which is the area under the curve of this function in terms of x, I'm going to estimate by using the midpoint with 5 rectangles. Midpoint is a rectangle. Finding the midpoint of the rectangle. So that formula was the change of x, 1/5 or 0.2, whichever one you want. I don't have to divide by 2. Times the height of the midpoint. Well, if this is changing by 0.2 every time, the midpoint would be halfway, 0.1. So my first x value right here would be 1/1.1. That's halfway between 1 and 1.2. And then, whenever you get that first midpoint, you could just add that to it every time. And because that's telling you how wide it is, so that's how wide it is to the next midpoint, plus 1/1.3, plus 1/1.5, plus 1/1.7, plus 1/1.1. That would be my last rectangle. Notice when I'm using rectangles, the pieces in here are exactly the number of rectangles. I'm using 5 rectangles, 1, 2, 3, 4, 5. But when I'm using trapezoid, in a minute when I'm using the parabolas, there's always one more. 1, 2, 3, 4, 5, one more 6. There's always going to be one more. So thank God we have our calculators, right? I have no idea what I'm going to do with ACP when they can't use their calculators to do this. This is why I'm dumb. Whatever. Huh? I mean, maybe they just stop here. I don't know. So anyway, we get about 0.691. Yeah, this is what they get to by the end of the semester. I don't know why they did this kind of thing. It makes no sense. Hey, just FYI, you don't know this yet. But the integral from 1 to 2 of 1/x dx will be very easy to find. You don't know that yet. You will be able to find this exactly pretty soon. And exactly is 0.693. That's what it really is. Hey, we got pretty close, right?
Midpoint.
And you can argue the midpoint was a little closer than the trapezoid. It's weird that the midpoint would actually be close. Both of them are pretty darn close. I mean, if you round it to do 2 decimal places, same thing. Okay, notice I'm saying that's what it really equals. Here, this is we're estimating. That's not so bad, is it? Not so bad.
Can you repeat that last part?
This one? Well, you know how to take the actual integral.
Yeah.
I just took the actual integral of this, and I got this. This is the real answer. These are our approximations using midpoint and trapezoid. And we see the midpoint's a little bit better. Okay. What's number 2? Use the trapezoid rule. Ooh, what if n equals 10? 10? Well, I did say more was better than less. And because we're gonna use our calculators, let's see, we're gonna estimate this from 0 to 1, e to the x squared dx. We're going to estimate that using the trapezoid rule with 10 trapezoids. Yikes. Okay, so we're going from 0 to 10, or 0 to 1, sorry. So I know my change of x is gonna equal 1 minus 0 over 10, every 1/10, or 0.1. This ain't showing up as much as I thought it would. So I'm gonna be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, all the way up to 1, right? Okay. So that is, I got my change of x, oh, I'm using the trapezoid, I'm using each side twice. So I got my change of x, 0.1 divided by 2. I know that's 0.05, but the calculator's gonna do it. And then I've got the first one, which is gonna be f of 0. That's my first side. And this is gonna be my last side. But everything else in between is gonna be 2 times. Plus 2 times f of 1.1 plus 2 times f of 1.2 plus 2 times f of 1.3 plus 2 times f of...
Wait. Isn't it supposed to be 0.1?
Oh, yes. We're going up to 1. I was thinking we were going up to 2. You're exactly right. Yeah, you're exactly right. For a minute, I was thinking 1 to 2, but we're going 0 to 1, so 0.1, 0.2, 0.3, 2 times, 0.4. Hey, if you're writing it down, I mean, in your calculator, you're gonna have to put it all in there, right? But if you're showing, hey, here's what I'm putting in my calculator, plus, plus 2 times f of 0.9, and then plus 1 times f of 1. Okay. If it's making sense to you, rather than writing this down 9 times, once you get the pattern, it's just like, hey, here's what I'm putting in my calculator. 2 times this one, 2 times this one, 2 times this one, 2 times this one. And then 1 times the last one. Thank God for the calculator. I didn't really show you what you're doing. Well, if you want to see what you're doing. Where's my trapezoid? Okay. I'm actually plugging it into this thing. So the first one would be e to the 0 squared plus 2 times e to the 0.1 squared plus 2 times e to the 0.2 squared plus 2 times e to the 0.9 squared. And then the last one plus 1 times e to the 1 squared. So I'm taking each of those values of x and just plugging it into. So there's what you're really doing. But it is fine, guys, if you do this like on an AP test. You know, show how you got your answer.
You can put it down.
Yeah. Once you are pretty sure, hey, this is the pattern. Plus, I really doubt if they're going to ask you to do 10. I've never seen that. But if they ask you to do 10 up, feel free
They ask you for 20.
to do that. And then where's my? Here we go. Where's my answer? Which comes to about 1.4. Yeah, 1.46. And I just put it in the calculator. That's all I did. See how tedious this is? If for some reason I was actually able to figure out the integral from 0 to 1 of e to the x squared dx, remember I said this is a symbol that will give you one value. This is the value it will give you, 1.44627. That's what it actually is. That's what I got by estimating with 10 trapezoids. Pretty darn close. Compare. Of course, you don't know this yet. I'm just showing it to you so you know. Hey, we're estimating, but we're getting pretty close. Pretty darn close. Hey, if I did it with 20 trapezoids, probably be even a smidge closer. Probably firm up some of these third and fourth decimal places.
You want to test out 20?
Yes.
Okay. You gotta get practice with this thing. It is, you thought the rectangles were. Oh, Simpson. Okay, so we got rectangles, 3 of them, left, right, midpoint. We got, well, what if we use trapezoids? Okay, we gotta tweak the formula a little bit because we're using both sides. So we're tweaking the formula. What if instead of a flat top to my shape, I have a curved top to my shape? If you're really interested, because that's gonna be a parabolic shape, on where this comes from, in your textbook, we'll show you. But I think it won't be mind-boggling so much, but if you want to see, hey, where'd that all come from? I can sum it up a little bit. So where is the Simpson's formula? What? Here's Simpson. Simpson's rule. From using parabolas instead of straight line segments to approximate the curve. And change of x is going to be b minus n. That's going to be the same. Okay. But what they're doing to do their parabolas, it's kind of like the midpoint. They're using the left we're using trap. They're going to use this, this, this. Oh my God, they're using more points. So here's Simpson. So S. However many pieces you're gonna have, still the same change of x. We're gonna make each width the same. Simpson, we're gonna divide by 3 instead of 2. Trapezoid divides by 2. But because we're using 3 points here, not 2, we're gonna divide by 3 now. And then, we're using this side once. Here's what you gotta do. The first one gets used once, the last piece gets used once, just like trapezoids. But trapezoids, you got everything 2 times, 2 times, 2 times, 2 times, 2 times. Here we alternate. Plus 4 plus 2 plus 4 plus 2 plus 4 plus 2 plus 4 plus 2 plus 4 plus 1. Yes. It is love. Mrs. Simpson. 4 2 4 2 4 2 4 1. Or specifically 1 4 2 4 2 4 2 4 1. So you start with 1, then you go to 4, and on the back end, you end with 1, and the one before it is going to be 4. Again, if you want to see the derivation of this, it's in the text. No. But there's one thing you have to remember besides the formula for Simpson's rule. I can only do it for an even number. It will not, if you do it for an odd number of pieces, it will not work out. You'll get 4 plus 2 plus 4 plus 2 plus 1. And it's gotta, once you start alternating the 4 and 2, it's gotta start with 4 and end with 4. So you gotta use an even number of pieces. You can't do it for like 5. No good. Somewhere I said that. Where is it? Oh, I didn't. Oh yeah, where n is even. Yeah, I'm sorry. It's right here in my yellow sheet. Where n is even. Okay. Oy vey. Who's ready to look at a Simpson? We could use the same ones we just did. Only do it for Simpson instead. Okay. I want the integral from e to the x squared dx from 0 to 1 dx. Oh, and you gotta put dx. This piece has gotta be in there. You can't just say this guy. No, can't do that. This piece gotta be in there because it's taking the place of change of x. We figured out the change of x, didn't we already? Right, the change of x was 0.1 from the last problem. We're using the same function. Okay, so if I'm gonna estimate this using Simpson with 10 pieces, that's gonna equal 0.1 over 3. And then my first one is going to be f of 0. No. Yeah, f of 0. And then I'll plug it in the next step. Plus 4 times f of, that's too many parentheses. 4 times f of 0. I almost did it again. 0.1. 0.1 every time. Plus 2 times f of 0.1 higher, 0.2 plus, can I just go dot, 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 plus 2 times f of, we'll figure out what that one is, plus 4 times f of, we'll figure out what that one is, plus 1 times f of, well, we know what that one is. That one's gonna be a last one. 0.1 before would be 0.9, 0.8. Following the same pattern all the way through. 4 times this one, 2 times that one, 4 times this one, 2 times that one. Specifically, it's gonna look like this. This is my width on the outside. So the first one I'm gonna plug into is gonna be e to the 0 squared. plus 4 times e to the 0.1 squared plus 2 times e to the 0.2 squared plus dot, dot, dot. Same pattern till I get to the end. 2 times e to the 0.8 squared plus 4 times e to the 0.9 squared until I get to the very end plus 1 times e to the 1 squared. Boy. 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Starts and ends the same way. However you want, if you want to try to put all this in your calculator one time, you can. When I started doing this, I did each little piece by itself. You know, I would do that one, get an answer, this one, get an answer, this one, get, yeah, I have 11 answers here, but then it was kind of easy to add up. It took more time, but depends on how you trust yourself with your fingers, I guess. Where's my answer to this one? Oh. Oh, shoot. Okay. Here I got 1.4627. Okay, what did I get before? The trapezoid one gave me 1.4604. I knew it was actually, I knew it was actually 1.4627. Look what Simpson is. I can't say exactly the same thing because, you know, the decimal place is down here, maybe changing. But man, you can at least say, man, Simpson's even better than trapezoid or midpoint. Yeah, I did. Even though it looks like it's exactly what it should be. Some of the decimals, we still want to say estimate because some of the decimals may be way down here, not quite the same. So let me ask you this, do we need to set up this one or you see how it's done?
I see.
Are you sure?
Yes.
You're sure?
100%.
Okay. Well, tomorrow we'll start off with that number 5. Hey, what happens if I don't have a function? I got a table. Remember, I love a table. Because if a table, I don't have to plug in this stuff to figure out these values. They've already given me the values in the table. Okay, so that's it.